Hi everyone. In this lesson, I'm just going to talk to you about a little sort of extra bit to the probability topic. Okay, so you've done tree diagrams with decimals and fractions, and you've done dependent, non-replacement, conditional probability, whatever you want to call it. Okay, where the fractions all change. This is a little bit easier, I would say, as long as you know what it is. Okay, it's not anything like as hard as non-replacement probability. So it's relative frequency, and I'll put this up. You'll need to write all this down, sadly, so if you want to just listen and write. It's a lot like probability, but whereas probability we sort of do it by counting what's on a dice, or counting parts of a spinner, or counting how many things are in a bag. Okay, relative frequency comes from actual experimental data. Okay, real life stuff where you've got no way of knowing the probability unless you test it out. Okay, and a good example would be that if I've got a factory and I'm producing little parts and I want to know the probability that one of those parts, when it comes off the production line, is faulty. Okay, faulty straight away, so I can't sell it, I can't use it. And you can't do that by looking in a textbook. Okay, the only way you're going to get that information is to actually run the machine and sit there and count how many it's made and how many of them are broken, and then you'll have an idea of what's going on in your machine, whether the 10% of them are broken, or 5% of them are broken, or 1% are broken. Okay, so relative frequency, it acts like probability, but it doesn't come from a book, it doesn't come from a calculation, it comes from actually some data. Okay, and as you'll know in science, when you write your conclusions to an investigation you've done, if you want reliable data, repetition is the key. So in relative frequency, the more trials you have, the more reliable your estimation is going to be for the probabilities for the relative frequency. Okay, if someone tells you that they did an experiment and they got heads every time when they flipped a coin, it wouldn't be very impressive if they'd flipped it three coins, but it would be very impressive if they'd flipped 50 coins. Okay, because we know that it's not that unusual to get 3 heads in a row, but it's practically impossible to get 50 heads in a row. Okay, and the key to that is knowing how many trials were done. Okay, right, so in my factory, to work out the relative frequency, I'd do a very simple calculation. I would divide how many broken things came off the production line by the total number of things that came off the production line. So if I tested 100 and 5 of them were broken, it would be 5 over 100. Okay, but in relative frequency, we don't work in fractions, we work in decimals. Okay, and if you don't really like working with decimals, probably the best thing to do in your head is to think of them as percentages. So my 5 out of 100 as a decimal would be 0.05, as a percentage 5%. Okay, when you've done enough trials that you're happy with your relative frequency and you think that it's accurate, then you can treat it like a probability and then you can calculate with it. Okay, but only when you've done enough trials to know that your numbers you're using are reliable. Okay, so here's an example then. And you have to pause the video and write. Sorry there's so much writing, but it's just one of those topics, probability, isn't it? So here's my example. If we sample 100 parts coming off the production line every hour for 5 hours. Okay, so I've got somebody sat on the end, and as things come down the conveyor belt, they just give them a quick test and they record how many are broken. And every hour they take 100 parts off the production line. So at 8 o'clock we took 100 parts off, 5 of them were broken. At 9 o'clock they took 100 parts and 3 of them were broken. And there's going to be variation because there always is, so it goes up and down. At 10 o'clock only 1 part out of 100 was broken. At 11 o'clock 7 were, so that was the worst hour if you like for having faulty parts. And at 12 o'clock in my last batch of 100 that I'm testing, 4 of them were broken. Okay. And while the factory owner would prefer that it's 1 out of 100 every time, look, it's as high as 7 out of 100. So you can't trust any of these results on their own. You've got to look at them all combined together. The more samples you look at, remember, the more reliable it is. Okay, so what we need to do with this data is make it cumulative. Remember, cumulative is when you add up as you go along. So I get the total number of samples and the total number of faulty parts. Okay, and by the end of it, I should have a fairly good estimate of what my machine is doing. So here's another table, but this time, look, I'm looking at the total number of samples. So at 8 o'clock we'd tested 100, by 9 o'clock we'd tested 200, by 10 o'clock altogether we'd done 300, and then 400, and we tested 500 altogether by the end of the morning. Okay, and on the top I'm going to fill in the total number of faulty ones I found. So by 8 o'clock we'd only found 5 faulty ones, by 9 o'clock we'd found 8, by 10 o'clock we'd found 9, by 11 o'clock we had found 16, and by 12 o'clock we'd found 20 out of 500. Okay, and to turn them into relative frequencies then, so underneath, remember the fraction is how many were faulty divided by the total number. So 5 over 100. Okay, if they're nice numbers you should be able to do this in your head. If they're horrible you might need a calculator. These ones are nice. So 5 out of 100 is 5%, 0.05. 8 out of 200, well that's the same as 4 out of 100, isn't it? So 8 out of 200 is the same as 4%, so 0.04. So the machine was slightly better in the second hour, look, and our relative frequency went down. Then we've got 9 out of 300. That's the same as 3 out of 100. So now we're down to 3%, 0.03. Okay. Now we know that at 11 o'clock we had a bad hour, so I can expect my relative frequency to start going up again here, look. 16 out of 400 is 0.04. Okay, 4%. And then 20 divided by 500, that's also 0.04. Okay, so we'd settled down in the end. We started off at a 5% sort of faulty rate. We were down as low as 3%, somewhere by the middle of the morning, but then we came up and we settled on 4%. Okay, 0.04. But I say them as percentages because it makes it easier to explain what these values mean, and it helps me later on when I want to do some calculations. Okay, the next thing we need to do with this data is to graph it, and I've put on a Word file that's got the graph paper to save your job. So if you've got a printer, open the graph paper sheet, print out the things, stick them in your book. Okay, it'll save you a job. You might need to resize them first to make sure it fits in your book. Okay, but what I'm going to do, so that's the same table we just had. It's the same values underneath, look, the relative frequencies, but I'm going to plot them into a graph and it'll show me what my machine was doing then. So at 8 o'clock when we tested the first 100, we had a 5%, 0.05 relative frequency, the probability of getting a faulty part. By 9 o'clock we'd done 200 and that dropped to 0.04. After 300 we dropped to 0.03, but then towards the end of the morning I'm afraid the relative frequency went up. We found a few more faulty ones, but actually what you can see and what we do on a relative frequency is join these up. To start with we wobbled a bit, but actually then we settled down, okay, and the graph flattened out, and that's not unusual. Okay, the more trials you do, the flatter your graph gets, until in the end you can say, well look, I can keep trying here and the graph's not going to wobble anywhere, so this must be a reliable number. And it's worth highlighting the very last one, because that last one is always your best estimate for one simple reason. That last cross there is for 500 trials, and more trials means more reliable. Okay, so if this asks you for which one is the most reliable or to pick a value and use it, always pick the last one if you get a choice. Okay, now then I'm going to answer some questions based on that graph, so I might have to do a little bit of scrolling up and down here. Okay, so part A, look, like I said, what is the best estimate of the relative frequency and why? So all you need to do there is write it in, 0.04, and the reason why is because it's got the most trials, so most reliable. Okay, every single time. The last one on the graph is the most reliable because it's got the most trials. Then my next question is a little bit trickier. It says, if the factory makes 8,000 parts per week, how many faulty ones would you expect? Okay, so this is expectation now when you try and predict what's going to happen for a whole week based on what we've seen just on one morning. Okay, so we said our best estimate was 0.04. You can think of that as 4%. So we're going to say that 4% of what comes off the production line is faulty. So if they make 8,000 parts in a week, this is like saying 4% of 8,000. Okay, well 1% would be 80, so 4% would be 320. So I would expect 320 faulty parts per week if they're making 8,000 parts a week. And now it's up to the managers of the factory, the bosses, to decide whether that's acceptable or whether they want to either repair the machine, replace the machine, or see what's going wrong. Okay, so this sort of thing is done day in, day out in factories across the world, checking the machinery, checking that it's reliable enough and what the machines are producing is good enough. And if they're not happy, then they'll either repair or replace the machines. Okay, so this is actual real life maths that does get done. Okay, right, when you're ready, press play and we'll go on to the next question. Okay, so this time the graph is drawn for us. Okay, but we've got some questions to answer. The graph shows the relative frequency of a carrot being deemed unsuitable for sale. Okay, and the inspiration for this question is a program I saw about the amount of food that gets thrown away because supermarkets say it's the wrong shape or the wrong colour. Okay, so we've got a graph. So the farmer has tested every 1,000 carrots. Look. So he's taken 4 lots of samples, so 1,000, 2,000, 3,000, 4,000, and we've got the graph plotted here. And I'll put some values on, and again, this graph is on the paper, so if you don't want to draw this in your book, you could just print it out. So that first value there, okay, these little squares are worth 0.02. Okay, so if you think of them in percentages, this is 10%, 20%, 30%. So on the third little marker there, is 26%, or as a decimal, that's 0.26. Okay, then we go up to 0.46, and then it comes back down to 0.4 and ends up on 0.32. Okay, those are the values. How many of the first 1,000 carrots were unsuitable for sale? Okay, so because the question is about the first 1,000 carrots, we look at the bit of the graph that relates to 1,000, which is here. Okay, so when he only tested 1,000, at that point in time, 0.26, 26% of them were unsuitable for sale. So I'm going to use the 0.6 value, okay, so times 1,000. So 26% of 1,000 is 260. Okay. If you take the value for 1,000. Now, is it the most reliable value? No, but it said how many of the first 1,000, so I had to use that first point there that marries up with 1,000 down there. Part B, what is the best estimate for the probability of a carrot being unsuitable for sale? Well, the best estimate is always the last one. So there's my best estimate. And that is 0.32. And why? Because it's got the most trials. Okay, I'd rather trust the data after 4,000 than trust it after 1,000. Okay, and then it says at the bottom then, part C, if a farmer harvests 20,000 carrots in a week, use your best estimate to work out how many would be suitable. So be careful here because it says suitable for sale. So we're going to have to do a little bit extra at the end. So we've already said that 0.32 is our best estimate. So 32% that is. So 32% of 20,000. So using our data from this sample, in a week, how many would be thrown away first of all? So this is unsuitable. and that's going to come out as 6,400. Remember, this is the ones which are unsuitable. That's what the graph is telling us. So now we can work out how many would be suitable. It would be 13,600 that are suitable for sale. Okay, I just took away from 20,000 at the end there to work out how many would be suitable for sale. Okay, and that pretty much covers everything you need to know about relative frequency. You need to know how to draw one. So make your data cumulative, make a little fraction out your numbers, convert them to decimals and plot them in a graph. If the graph is drawn for you, read decimals off from your graph and then apply them to any questions underneath. And the last coordinate on the graph, the last data point, is the most reliable because it's got the most samples. Okay, so hopefully you've got everything here in your book. I know it's probably taken you a while to draw the graph, so thanks for sticking with it. And have a go at the questions in the booklet which is attached to the lesson.